check, check, check. There we go. My hair is crazy. I just posted the notes. If anyone's willing to follow along with the printable notes and print those out or open them up on an iPad or something like that. Add. Didn't have a 1.5. Go. Alright, how we doing? Who's in the chat right now? Anybody? How's life? How we doing? Okay. I'm gonna give it till 2 before I officially start, since that is when I usually start, so. Chatting here. Anyone in the chat right now? Just me? Just me alone with my crazy hair? What up? How's it going? How's it going? You're adopted. Shouldn't it be YOU''RE? It's going pretty good. I wish I would get more viewers live. The replays have still been getting quite a few views, so I have that going for me, but get some more live people in here. Hey Google, turn on the bedroom lamp. Alright, it is 2 o'clock, so whether I'm doing it to myself or whether there's people listening to me, I ought to probably start the lesson. So, right about here is where I'll start the lesson. Hello, geometry folks, tuning in and watching this replay or watching the live stream right now with me. We are about to do lesson 2.1 notes. Okay, so if you've been able to print out those notes, that's awesome. They're printed, they're available in the Canvas module 2.1 printable notes. Don't forget to do the live stream assignment 2.1 to let me know that you did indeed watch. I really appreciate those who do those and let me know that they are watching. Yeah, here we go. So thank you for tuning in. maybe go over homework for more viewers. Yeah, maybe so. So we're looking at angles. An angle is, a guide that looks like this. It opens up, and there's some type of measurement here. How big is it? I don't know. But an angle is formed by two. What are those guys shooting out in opposite directions? We call those rays, right? Rays are these almost like lines, but remember, lines are in an infinite direction, rays are in one direction. So those are two rays that are going out and opening like that. The common endpoint is called the vertex. So this point right here is called the vertex of the angle. And the rays are called the arms or the legs or whatever you want to refer to them as. Um, I'm going to refer to them as what should I refer to them as? I'll just call them the sides. Okay. So this is a side and this is a side. So, what are the types of angles that we often see? There's small angles, there's big angles. These have names. Acute angles are angles that are between 0 and 90. Right angles are exactly 90. Obtuse angles are between 180, and straight angles are those flat, essentially look like lines. They're exactly 180 degrees. Do whatever it takes to remember those. Something cute is usually small and tiny, so that's between 0 and 90 degrees. I think a lot of us know what right angles are. Obtuse, well, number one, obtuse is a longer word than acute, so it's bigger. Obtuse is kind of I don't know, it's kind of a weird word. Whatever helps you remember, that's between 90 and 180. And then straight, right? I think we all know what the word straight means, a straight flat line. That's exactly 180. So whatever it takes to remember the difference between those words. So we're just looking at an angle here. This angle has 3 points, F, Y, and S, and we want to name the parts of this angle. So the vertex is point Y because that's where the rays are sprouting out from. So we call that the vertex. And then the sides of the angle are those two rays, which is the word I used up here. So the sides are YF and YS. And how do we label rays? With a single arrow over the top, like so. Um, that is not the same thing as FY, if you remember that, right? This would be saying that the ray is sprouting out from F and going towards Y. That's just not the case here, okay? So that's an incorrect way of naming it. It has to be YF and YS. And then what can we actually name this angle? Well, let's look over here off to the left, naming angles. We can name angles two different ways. Using the 3 points that kind of combine to make the angle as a whole, or we can use a single point, but we can only use a single point in certain situations. So let's do the two easy ones using all 3 letters. So I could call this angle right here, angle FYS. I'm starting here and going around the angle, so to speak, right? I'm going in that direction. And then I could go the other way around. Oops. And I could also call it SYF and go that way around the angle. Either way, take note that let me actually highlight, that the vertex is the middle letter for each of those. That's always the case. And then in our notes off to the side here, it says you can use 1 point only if there is a single angle with that vertex. As far as I know, looking at this page, there's only one angle, that one right there. There's no other angle that has point Y, okay? So we can simply call this angle Y. Let's name some more angles, okay? So over here, the vertex for how many angles are actually are in this picture right here? That's actually a good question to start with. How many angles are in picture number 2? 1, 2, and 3. There are 3 angles, the 2 small ones and the 1 big one. However, all 3 of them have the same vertex, point A. So if I were to name, I'm going to skip I'll name the sides real quick. Let's go ahead and do that. The sides are pretty obvious: AB, AC, and AD. Okay. Now, if I were to name that, I'm going to refer to it as the purple angle, right? If I were to name that purple angle, again, you go in around the angle, whether in a clockwise or counterclockwise motion. I could name it angle BAC or angle CAB. Either or makes sense. C to A to B or B to A to C doesn't matter. You're going around the angle. And again, take note that the vertex is that middle point. If I were naming the blue angle, angle CAD, or I could call it DAC, either or makes sense. And lastly, for the green angle, I would call it angle BAD or angle DAB. Again, doesn't matter which order you choose to go around it, as long as, like I said, that vertex is always going to be in the middle. Now, can I name any of these angles with a single point? Right? I can't name these angles with a single point. They all share a vertex at A. If I were to simply show you this picture and said angle A is 42 degrees, which one am I referring to? The purple angle? The blue angle? The green angle? They all have the same vertex. That's not specific enough. So it's not possible to name it with a single point. Only when there's no ambiguity is the word I like. Ambiguous meaning like if something's ambiguous, it's like unknown or fuzzy or hard to determine, right? I think it's pretty obvious that if I were saying angle Y, I'm only talking about this one angle. What other angle is there, right? There's only one on the page. So I can simply call it angle Y. Naming is something that's very important, right? We started this class naming lines, right? And segments. Naming stuff, we need to be able to talk about these objects and not be confused as to what we're looking at. Naming things is honestly pretty important. So we want to make sure we get those names down and know the proper way to order our letters. So, how many angles have point A as a vertex? Here's point A. It appears there's only the one. How many have point B as a vertex? It appears to be 1, 2, 3 angles have B as a vertex. How many have point C as a vertex? That I could have this angle, I could have this angle, and don't get it confused, right? The straight angle ACD is also an angle. So this whole big thing, once again, there's 3 angles. I can look at that again. I kind of scribbled a little bit, right? There's this angle here, There's this angle here, and then the whole big one. So there's 3 there. And then at point D, there's only the 1. What is another name for angle A while we're here? Why can I refer well, first of all, why can I refer to this as just angle A? Because there's only one angle. But I could also name it angle BAC if I wanted to, right? B to A to C. Or I could just call it angle 4, right? I mean, it's been labeled on the page. I could just call it angle 4. Yeah, this is Geo. It looks kind of like 24. Angle 4. What is another name for angle ABC? A to B to C. A to B to C would be this guy right here. So obviously I can call it angle ABC. I could go backwards and call it CBA. I could also call it angle 1. Any of those would be correct. How about I write the easiest one, angle 1? That's pretty short and sweet and to the point. What type of angle is ACD? That was the one I told you not to miss as I was labeling them, right? ACD is a straight, flat line. I just used the word. It is a straight angle. Meaning it's equal to 180 degrees. That's why we're calling it a straight angle. Let's knock out some solving ones real quick. So, uh, we saw the segment addition postulate during our previous lessons, where, okay, if I give you a segment that is broken up into 2 smaller segments that are, say, 4 and 11 long, well, the segment addition postulate says, well, just go ahead and add those 2 together, and you know how long the big thing is. It was really that straightforward, right? Or I could go the other way around and say, like, okay, the whole thing is 12, and this piece is 4. How long is this one? Well, 12 minus 4, that means the remaining piece must be 8. Those were the type of problems that we saw with the segment addition postulate. We're looking at the exact same thing for angle addition postulate, okay? Literally, except we're talking angles instead of segments. So let's say this is angle 1, and this is angle 2, and then we'll call this A, B, C. Well, the angle addition postulate says angle 1 plus angle 2 equals angle A, B, C. The sum of the 2 smaller angles add up to be the big one. Just like the sum of the 2 smaller segments add up to be the whole thing. I'm using the exact same logic. These 2 smaller angles add up to be the entire angle. Pretty straightforward thought. So with that being said, how big is FDC? It's just a combination of 21 and 23. Easy. It's 44 degrees large. If we were to fill in this equation right here, what we're saying is that angle FDC is the sum of the 2 small ones, ADC and ADF. Let's fill in the equation again. What we're saying is that the large angle EDC is the sum of the 2 smaller angles, this guy and this guy, put together, which is FDE and FDC. So That's what we got, but take a look at what 130 is labeling. 130 is labeling the entire piece, right? It's labeling the entire thing. And we, sorry, did I say FDC? I meant 130. I don't know what I said. Let me back up and say it again. 130 is labeling this entire thing, and that's EDC, and we're trying to figure out FDC. So we're actually going to take the 130. Hopefully this makes sense, right? I'm going to take the 130, subtract away this piece, and it ought to tell me with what's left. Take a look at our equation too. If this makes sense, if this equation makes sense, how would you solve for FDC? Right? I want to solve for this. That means I need to subtract this guy to leave me with just this, right? You see what I'm saying there? So actually, better yet, let's write the equation. So EDC is 130, FDE is 82, and I want to solve for this guy. Maybe you're watching this and you're like, Mr. Skis, it's very easy. Just subtract the 82. I'm just making sure we're all on the same page. Okay? So 130 minus 82 is, pull out my calculator, google.com, 48 degrees. Perfect. So, I mean, that ought to feel like deja vu, except we're looking at angles instead of segments. Because, I mean, literally is the exact same thing. Angle addition postulate and segment addition postulate are long-lost twins, okay? Toss in a little bit of algebra. Let's toss in a little bit of algebra. We want to solve for POQ and QOR over yonder here. But before we can do that, we kind of need to know what X is. So let's write an equation that is true about this particular drawing. We know that POR is the sum of these two small angles put together. Let's go ahead and draw that out. POR, that's a 2. POR is the sum of the two smaller angles, POQ and ROQ, put together. I don't care how you name it. Maybe you were like, well, Mr. Skis, I was going to name it QOR. Go for it. I don't care. But what we're saying is that the large angle POR is the sum of these two smaller ones put together. Okay? Should I write that a little cleaner? My handwriting's a little bad on those two. POQ and QOR. So, with that being said, POR is 78. I mean, it says it right there. POQ is 7x minus 6. And QOR is x plus 12. There's my equation, right? The equation says the big angle is the sum of the two smaller ones. I understand that there's some x's everywhere, but don't let that intimidate you. You know what you're doing. You know that statement is true right there. So let's go ahead and add up our x's. 7x and x, that's 8x. Minus 6 plus 12 is positive 6. 12 minus 6 is 6. Combined these like terms. Okay. I need to solve for x, so I'm going to subtract the 6. And I'm going to end up with 72 equals 8x. Divide the 8. And I'm going to end up with 9 equals x. So, with that being said, let's plug in x. So, QOR is x plus 12. So, therefore, 9 plus 12 gives me 21. And then, so QOR is 21. And then POQ is 7x minus 6, and x is 9. So 7 times 9 is 63. 63 minus 6 is 57. And do a double check here. Is 21 plus 57 equal to 78? You betcha. All right? That's what it was supposed to do the whole time. You betcha. It worked out. We got the 2 right answers. If it didn't add up to 78, I mean, that defeats the whole purpose, right? The 2 smaller angles should be adding up to the big one. Um, should I leave this one? Let me leave this one, and that'll be one that I can do maybe during the time that we have during class. Um, yeah, I'll go ahead and leave that one blank. Go ahead and, if you're watching this video right now, hopefully you haven't left me, you're watching this video still, go ahead and review my thoughts on this. Rewind 2 minutes. If you want to see this again before class, right, go ahead and rewind 2 minutes and just get my train of thought there. Like, I think we're all pretty good with algebra. It's just that you might not have the confidence to write the equation, okay? I believe in you. Believe in yourself. You can write that equation. Just think it through, and then I'm confident that you can solve for 9. I'll leave this one for class, though. Let's do one other thing, and then we're done, right? Because this is the last page here. Let's talk about bisectors. And I'm going to pull up this link here. mathopenref.com/talk/constructions talk HTML. 404 not found. Let me type it one more time. Uh-huh. Got it. Okay. So, what angle bisector? Bisect an angle. Okay. So, here's this step by step. Can I like go full screen or something on this? So here's this guy here. Let me hide my webcam. Hide that real quick. Okay, so bisecting an angle is the act of splitting an angle in half. Typically in geometry class, we would do constructions, but it's a little hard to do constructions virtually. So this right here is a step-by-step process of how we would construct something with a compass in class. So they would take the point of the compass and put it on the vertex, and then you stretch out the compass to just some random arbitrary spot along the arm or the side of the angle. And you would draw an arc on that leg and on that leg, right? So the distance from Q to this arc and Q to this arc are the same. From where an arc crosses a leg, make an arc in the angle's interior. So we're going to put the point of the compass right here and draw another arc out in the center, and then we're going to do the exact same thing from the other side. What happened is that by doing this construction, we just found a point that's exactly in the middle, and if we draw a line, all of a sudden we have a an angle bisector. Bisector meaning to split into 2. Bi meaning 2, sector meaning like split sort of. So bisector, and these 2 angles are the exact same degree measurement. Okay? This angle on the left is the exact same measure. So 20 and 20, 30 and 30, 25 and 25, 60 and 60, whatever it is, These two angles have the exact same measure. This pink line perfectly splits it in half. Um, so, it literally just means to split in half. So if I gave you an angle L A B, and AH is the bisector, and the whole thing. Whoa, what just happened? And that's an H. This entire angle right here, L to A to B, is 120. Well, then how big is each half? 120 divided by 2. They're each 60, right? Don't overcomplicate this, okay? A bisector means to split in half. What is this line that's right there? Weird. Has that always been there? Okay, so use the figure to the left. OH is the angle bisector of DOS. So if it's the angle bisector, what we're saying is that angle DOH, the measure of angle DOH is equal to the measure of angle HOS. That's what we're saying. This guy and this guy are the same. And remember, I use the little tick marks to say that something is congruent or to say that they are equal. Okay? So those two angles are the same. We don't know how big they are, but we know that they're the same. So what have we been given? DOH is 5x minus 16. And SOD is the entire thing. 3x plus 10. You're watching the replay right now. Listen to this question. How big is SOH? It's not a number. I'm not looking for a number. I'm not looking for a measurement. It's on the page. How big is SOH? It is 5x minus 16. Don't overthink it. It's the exact same thing as DOH. I don't know how big DOH is. I don't know how big SOH is. All I know is that it's quote unquote 5x minus 16 big. So with that being said, what do we know? What does the angle addition postulate say? It says add the two smaller angles, even if they're the same. Add the two small ones, and together they make the entire thing, which is how big? 3x plus 10 big. And solve. 5 and 5 make 10x. Negative 16, that's negative 32. Add the 32 over, you get... Subtract the 3x over, you get... So therefore, x equals 6. That might have been a little bit of a thinker there, especially to come up with this, right? I gave you maybe I didn't give you enough time to think that through, but I'm not trying to make the video too long. But if this was no different than the previous example up here, right? It's just that these two measurements happen to be the same, but nonetheless, add the smaller angles together and that should equal the big one. So we got x is 6. Let's just plug everything in. DOS, or in other words, SOD, that's 3 times 6 plus 10, so 828. DOH, that's 5 times 6 minus 16, so that's 30 minus 16, so that's 14. And then if DOH is 14, well then SOH is 14. And together, 14 degrees make 28 degrees. There's a few of you watching. Those of us watching, do we have a question? I've completed the geo notes. I'm going to leave this one example up here to do in class. Does anyone want to ask a question? I'm more than willing to chit chat with you. I appreciate you taking the time to watch live. I want to help you out if there was something that stumped you, or if you just want me to scroll back up to something, you let me know. All right. Well, those of you, if you're still watching live, thanks for tuning in. If somehow you're still on the replay even after that lull of silence, I appreciate you watching. Don't forget to fill out the live stream assignment 2.1. I'm going to make an announcement for Algebra 2 live on Twitch starting. I'll just say live on Twitch. Then 2.1. Yes, Twitch. All right. For this one, what am I doing? All right, I'll give just a minute or two here for Algebra 2 people to trickle in. I'm going to pull up my Algebra 2 notes. We're doing a lot of Desmos today. I need a better scene for Desmos, to be honest. When I do Desmos, it just kind of... Well, really, my webcam... I'll fiddle with it right now. My webcam should go over here. Probably. Probably a good spot to put it. Then chat can still live its life there. Although you can't read the chat because of the white background. Do that, I guess. We got the banger lo-fi beats. Is anyone still out there right now? Has anyone joined? Is anyone ready for Algebra 2? If someone's out there and want me to start Algebra 2, we'll just start. Did I post the... Ooh, I need to publish the module. There we go. Hog Math, what's up, Alexandro Sauce? How are you doing? Are you for Algebra 2 or are you just a stranger in the world? I'm doing good. For Algebra 2? Okay. Do anything this weekend? Really? Feel that. I saw Tenet again in theaters. Recommend that movie. Pretty dope. Alright, should we boot it up here? Alright. So you're watching live, you're watching the replay. Algebra 2 starts now. Thank you for watching. Make sure to follow along with the printable notes, which are published on Canvas. I recommend doing it that way. Or just taking notes in your own notebook. Fill out that live stream assignment 2.1. That does make things nice and easy to keep track of for me. I appreciate when people do that. And yeah, we are solving quadratics by graphing. We're going to be using Desmos like none other. So let's just read this blurb and try to get a grasp on what it is that we're doing. So solving quadratics by graphing. The zeros of a function are x-intercepts of its graph. We know that already. These are the zeros, okay? Very identifiable points, okay? It's the points that intersect the x-axis, okay? They are x-intercepts. They are the zeros. They are called the zeros because y is equal to 0 along this line, okay? Up here, y is equal to 1. Up here, y is equal to 2. The point is, right here, y is equal to 0. So we call them the zeros. If a function is equal to 0, then the zeros of its graph are the solutions to the equation. In other words, the solutions are the intersection points of the graph of the equation and f of x equals 0. So what we're saying is, here's this function right here. That's this graph right here, okay? This function is this graph. What if we wanted to solve the equation x squared plus 5x minus 6 equals 0? This is a function which is graphable. This is an equation that we can solve, and there are two answers. Those two answers are 1 and 5. Because that's where the function is equal to 0. Hence those 2 points being called the zeros. Okay? So if you want to solve an equation that is set equal to 0, the zeros are the solution. Let me say that again. If you want to solve an equation that is set equal to 0, the solutions to said equation are those points that we refer to as the zeros. Okay? Because watch, if I plug in 1, let's say, 1 squared plus 5 times 1 minus 6. That's 1 plus 5 minus 6. 1 plus 5 is 6. 6 minus 6 equals 0. 1 is a solution to this equation. Let's do it again. 5 squared plus 5 times 5 minus 6 equals 0. So 5 squared is... Wait, that's not going to work out. That's embarrassing. Hey, that's not going to work. Is that a graph right? Yeah, that's not graphed right. There's a typo on here. That's a typo. This graph is not plotted correctly. This graph is not plotted. Oh, this is a live interaction, live error. This graph is not plotted incorrectly. This should be crossing at -6 over here. The other solution is -6. Check this out. So it's not 1 and 5. This is wrong. This is a typo right here. That's wrong. The other solution is at -6. Here we go. I'll plug it in real quick. -6 squared plus 5 times -6 minus 6 equals 0. So I get 36 minus 30 minus 6. So 36 minus 30 is 6. 6 minus 6 equals 0. I'm sorry, I'm cramming it over here into the corner. You see the error that I just caught? That's how you can actually check your answer. Look at what I was about to do. I was gonna put in 5 squared plus 5 times 5 minus 6, and I was gonna say, is that equal to 0? 25 plus 25 minus 6 does not equal 0, right? That's gonna be 50 minus 6, that's 44. So that's obviously not one of the solutions. So the answers are 1 and -6. We just caught an error live. How fun is that? Okay. Fix this. Okay. Nonetheless, let me say that sentence one more time. If you are setting an equation equal to 0, the solutions are the points at which your graph crosses the x-axis. Those are referred to as the zeros. So look at this function right here. What's happening to that function? It's been moved left 4, down 3. And it's been stretched by a factor of 3. So it's super skinny like so. For the sake of time and because we all have Desmos at our fingertips, I think we should use it. So let's use it, okay? I just plotted it by hand, but some of us are going to be better by hand, and others of us just want to go ahead and use Desmos. So here is this function, okay? I graphed the entire function, but where is it equal to 0? Okay? Where is it equal to 0 is the question, right? Looking at the equation here, we want to know when is it equal to 0. Again, I say it one more time. The solution to this equation is the zeros of the graph. Because we're trying to find where is it equal to 0. So find the zeros. Boom. It's equal to 0 here and here. So the two solutions are at -5 and -3. It's that easy. That's at -5 and that's at -3. The solutions are -5 and -3. So plot this graph. Wherever the zeros are, those 2 points are your solution. What has this done? This has gone up 9, and then it's been flipped. Again, a quick sketch like that, I mean, where exactly is it intersecting? I'm drawing it so quickly. It is just a sketch. It's just an approximation, okay? It's not exact. What's up, Q? How you doing? So when I look at the graph, where does it cross the x-axis? Right here and here. So the two solutions are -3 and 3. It's that easy. You plot the graph and you check where is it crossing. I can even plot the line. Where is it crossing y equals 0? They're intersecting here and here. So my two solutions are -3 and 3. Okay, so what happens when a function isn't equal to 0? What can we do? What should we do? What can we do with Desmos to make that easier? If a function is equal to something other than 0, then the solutions are the intersection points of the graph and whatever that new line is. So this is the line y equals 0. This is the graph that I just graphed, and their intersection points are the solutions. And I said those are the zeros because y is equal to 0. But in a solution, or in a situation, I should say, where I'm not looking for the zeros, but instead I'm looking for where it's equal to 6, instead of finding where it crosses the x-axis and where y is equal to 0, how about we find where it crosses the line at y equals 6? So let me draw the sketch before I move to Desmos. Left 1, down 3. And I'd do a quick sketch. Again, I'm not crazy about how accurate we do this. I don't want to know where it's equal to 0, okay? That's not what I want anymore, right? Because it says equal to 6. I want to know where is it equal to 6 instead of 0 now. You see the difference here? These examples up here, I wanted to know when it was equal to 0. So I was like, oh, it's at 0 along this line right here. Well, when is it equal to 6? 6 is along this line. I want to know when my function's equal to 6. So let's plot that on Desmos. So we've got x plus 1 squared minus 3. And we want to know when is it equal to 6. Y equals 6 is the horizontal line at 6, okay? Just the straight up number 6. If you typed x equals 6, it's a vertical line, okay? So y equals 6 is this horizontal line. So where is this green graph equal to 6? Here and here. So our two solutions are at -4 and 2. It's that quick. It's that easy. We love Desmos. We love Desmos for that reason. Um, so this is in intercept form. It tells us that we have zeros at -5 and -2. But those aren't the points that I care about. I care about the points where the graph is equal to 4. The graph is equal to 4 along this line. So, what is the value? What points are here and here? Again, I'm just doing a rough sketch. You can't really trust my rough sketch to be super accurate, so I turn to Desmos because it's my trusty friend here. So there's that graph. You can see it has zeros at -5 and -2, just like I sketched. Except now I want to know where is it equal to 4? Right here and here. So what are our two solutions? -6 and -1. It's really, whoops, I'm in highlighter. It's really that quick, people. It really is that quick. You gotta love it. You gotta love it. Um, should I even do one more? I don't even want to do one more, right? I've already done four of them. I'll leave two for class or something. Okay? Let's make this super quick, right? No stress, right? You plot the left half. No, look at what I'm doing. I'm plotting the left half and I'm plotting the right half, right? That's what I'm doing. I'm looking at the left half, plot it. Looking at the right half, plot it. Where do they intersect? Looking at the left half, looking at the right half, where do they intersect? Should I write that down in words? Let's do it. Plot the left and right separately. Where do they intersect? That is your solution. Right? That's what I'm doing each time. Okay, so let's take that logic and apply it to a word problem. Which one should we do? Or do we do both? Maybe we do both. We'll see. So, from 1970 to 1990, the average cost of a new car C in dollars can be approximated by the model. I'm going to type that real quick. I know you can't see what I'm typing, but that's okay. 30.5. Now, what's interesting here is that I understand that they're using T and C, but you need to realize that Desmos does not understand that. That's the same thing as this, okay? Desmos only works in terms of X and Y, okay? I understand that the problem's being kind of clever and using T and C, but you need to realize that Desmos only likes X and Y, okay? So I've plotted it on Desmos somewhere. Where's it at? There it is. I'm gonna pull it up so that way you have it here. So this is so the y-axis is cost. It was a capital C, but now I'm using X and Y. And this is time. Okay, the years, I should say. Years since 1970. During which year was the average cost of a car, new car, $12,000? So we want to know what is the X value that satisfies this equation, right? That's all we care about, right? When does the cost of a car equal 12,000? Not just some generic value. I want to know at what moment in time does it equal 12,000? So here is the graph. So what we've got here is that year one, or whoops, this graph is sort of obnoxious. Did I change the scale? Let's change the scale. Um, how about I make the steps of the x-axis something like 100? It's kind of sorry. It's just kind of weird the way I'm having to zoom in to like see the trend of the graph. So this graph represents the cost of a car. So I know it's so skinny. So as well, my x-axis is so weird. I don't know. I'm trying to. It's kind of hard to show the trend of the graph at the same time as like here. How about I do this? I don't even really need the left hand side of the graph, right? And then I'll do like 20. There we go. Okay. Sorry about that. So when 1 year passes, the cost of a car is now what, $4,200. When 3 years passes, it's now up to 44,500, right? When 6 years pass, it's now up to about 5,300. When 10 years have passed, it's now up to about 7,000. So when is it equal to 12,000 is the question. Right there. After 16 years, the value of a brand new car is up to $12,000. Again, this graph represents the cost of a new car as time goes by, right? Because of inflation, right? You could buy a new car back in the day for like pocket change, right? Now, brand new cars are $20,000, right? So it wasn't always like that, right? So as time has passed, costs of cars have gone up. So after 16 years, the cost of a brand new car was $12,000. What does that mean in the context of this problem? X equals 16. Whoop-de-doo. What does that mean? During which year was the average cost of a new car $12,000? It definitely wasn't in the year 16, right? That doesn't make any sense. What does X represent exactly? The number of years since 1970. In other words, in the year 1986, a car was $12,000. Um, what? It's a bonus question. What X value represents us right now? 80, 90, 2000, 2010, 2020. We're 50 years since 1970. So let's look at the graph. What represents us? 50 years since 1970. This function predicts the price of a new car would be not very accurate. A price of a new car is not $80,000. So this is only so accurate, right? It's accurate for a time, and maybe prices of cars were really shooting up back then, but now prices of cars have kind of leveled off. Let's do the last one for good measure. You toss a ball into the air at a height of 5 feet. The velocity of the ball is 30 feet per second. You catch the ball 6 feet from the ground. From the ground, not for the ground. You toss a ball into the air at a height of 5 feet. The velocity of the ball is 30 feet per second. You catch the ball 6 feet from the ground. Use the model 6 equals negative 6t squared plus 30t plus 5 to find out how long the ball was in the air. Um, Thank you, Alejandro or Alexandro. Um, okay, so let's check it out. I'm just was just trying to interpret the question for a second. You toss a ball into the air at a height of 5 feet. So we're right. We are like 5 feet tall, right? We're tossing the ball from a height of five, so it doesn't start on the ground. That's kind of the catch here, is that the ball is not starting on the ground, right? And you don't catch it on the ground, right? You're catching it 6 feet from the ground, okay? So it's not about whether it hits the ground or not. This graph represents the amount of time it was in the air. So we want to solve this equation, okay? because what this graph is representing is the fact that we're tossing the ball from midair, and the ball is going to be thrown from here and caught here. Okay, it's not touching the ground. Okay, it's leaving our hands from up high and landing in our hands from up high. Okay, it's not touching the ground. That's why this isn't set to 0. Okay, I'm just trying to help you understand that equation and where it's coming from. We've got this arc of a ball, but that arc, it's never actually touching the ground. Okay, so let's take a look at what this arc